Hello there. In this video, we're going to begin our discussion of another family of functions that is often used throughout the realm of calculus and, of course, pre-calculus. So let's just firstly define what that is. So let us suppose that P and Q are polynomial functions. Then we're going to define the function f of x to be equal to p of x divided by q of x. So this function here, namely the quotient of two polynomials, is what we refer to as a rational function. So this is the type of function that we're just going to be talking about in this video and the next video, and we're going to talk about a few properties and characteristics associated to these functions that possibly the polynomials and some other functions may not have. Alright, so before we make things super complex and difficult, we're just going to begin by looking at the basic rational function 5x is equal to 1 over x. So we're just going to look at a couple characteristics for this particular function, because you're going to notice that some of the characteristics for this very simple looking rational function is actually going to carry over into the more complex representations of rational functions. So one should be able to find that if you plug in 1 and negative 1 into this function, you're going to get 1 and negative 1 respectively. As you make x an extremely large but positive number, you're going to notice that the numbers definitely do decrease and get closer to 0 but never touch it. As x gets close to 0 from the right hand side, so 1/2, 1/4, 1/8, 1/16, and so on, you're going to get closer and closer to something really, really large, right? Now, why is that so? So if you do 1 over a half, 1 over a fourth, 1 over 1/50th, 1 over 1,000. So what happens when these numbers x gets closer to 0 from the positive side? Well, 1 over something is just the reciprocal of that. So this is going to be 2, this is going to be 4, this is going to be 50, and this is going to be 1,000. So as x gets close to 0 from the positive side, the value of y gets arbitrarily large. So if you graph those points and connect them, you should get some representation like that. So you sort of have this U turned at an angle. And you can do the same exact analysis for the negative side, and you're going to get something that looks like this. So this is the graph of the function phi, where the horizontal is x and the vertical is 5x. All right, so let's just write down a couple properties that we use to sort of construct this graph, because all of these are going to be really important later on. So the first property, so as x gets closer to positive infinity, and keep in mind positive infinity is not a number, it just means as x gets arbitrarily large. So as x gets arbitrarily large, so as x gets arbitrarily large, the value of phi of x is going to get closer and closer to 0, right? Because notice that this is definitely decreasing, right? So that's the first observation that we should be able to see. Also, as x gets close to negative infinity, and again, what does this mean? So this is equivalent to saying as x gets arbitrarily large in the negative direction. So the first one is of course positive, right? So as we move closer and closer to the left side of this graph, the value of y, so it starts off a really negative number, then it gets close to -1, then -1/2, -1/4, -1,000, and it gets closer to 0, but from the bottom side. So therefore, as x gets close to negative infinity, what happens to the value of 5x? Well, 5x is going to get closer to 0 as well. right? So we can combine these two statements into one. So as x tends to plus or minus infinity, 5x, which is equal to 1 over x, is going to tend to 0, right? So let's write down a couple more properties that we have. So 3, as x tends to 0 from the right side. So what do I mean by that? So if we reference our graph from before, so this is our curve. So as we get close to 0 from the right-hand side, so we're going to be approaching the positive y-axis. So as x gets close to 0 from the right-hand side, and you may see some people write this as x tends to 0 with a plus sign sort of in the exponent, then the value of 5x is going to get close to positive infinity. Again, positive infinity is not a number. This statement just means x gets arbitrarily large in the positive direction. And similarly, as x gets close to 0 from the left side, and again, you may see some people write this as x gets close to 0 with a negative sign, sort of in the exponent, then 5x is going to get close to what? So if we approach this from the right-hand side, notice that this curve definitely sort of goes down the negative y-axis and gets arbitrarily large in the negative spectrum, right? Cool. So let's look at these two sets of statements in a little bit more detail in regards to this graph, right? So let's draw our curve. So we have this curve here and this curve here. So there's these two lines, right? So there's this line that this curve approaches but never touches, right? So it approaches 0 from the positive side on the right and it approaches 0 from the bottom side on the left-hand side. So it approaches this blue line. So if we sort of extend this axis outward and extrapolate our curve outward, this curve is going to get really, really close to this line, but it's never actually going to touch it. So we usually refer to this line as a horizontal asymptote. So it's a horizontal asymptote. It's horizontal because it's definitely, laying on its side. And this word asymptote means it's just some curve or line that this curve approaches but never ever touches, at least in the finite spectrum. And this horizontal asymptote in this case is of course the line y is equal to 0. In a similar fashion, we have a vertical line on the y-axis. And if we sort of extrapolate this outwards and extrapolate our curve drawing, again, this curve, 1 over x, is going to get really, really close to this green dotted line, but never touch it. So take a guess of what this line is called. So this line is going to be called a vertical asymptote. And in particular, it's the line x is equal to 0 because it is the y-axis. So a lot of rational functions, so just a note here. So a lot, and I'm going to put a lot here because I'm not going to go ahead and claim that all rational functions have horizontal and or vertical asymptotes, but a lot of rational functions have asymptotes of some form. They could have one horizontal asymptote, two vertical asymptotes. You could have what we call slant asymptotes and parabolic asymptotes. We'll get into these more intrinsic details later, but overall they have these lines or curves that the rational function approaches but never quite touches it. And also let's mention the domain and range, because from the asymptotic perspective we should be able to state what the domain and range are. So if we take a look at our graph of 1 over x, so it definitely does cover all x values except for 0, because you cannot divide by 0 in the expression 1 over x, so x clearly cannot be equal to 0. And if we sort of switch this around and write it in terms of x, so we have x is equal to 1 over y, so clearly y cannot be equal to 0 to have a corresponding x value either, right? So we can say that the domain of phi, where we're defining 5x to be equal to 1 over x, is going to be equal to the set of real numbers except x is equal to 0. So you can rewrite this as the set of numbers negative infinity to 0 to 0 to infinity. So keep in mind x belongs to this interval. And the range of this function is going to be the set of real numbers except 0, the horizontal asymptote. And again, you can rewrite this in interval notation as minus infinity to 0 union 0 to infinity. And remember, we're talking about y values in this corresponding expression. So let's just take a look at a couple rational functions to sort of make sure that we understand all the main components of this. So let's consider f of x is equal to negative 2 divided by x plus 3 plus 5. Let's see if we can graph this and sort of understand the main components of this function. All right, so as x tends to infinity, what happens to this function? So if we look at this expression here, which is the only part that actually has x in it, as x gets big, x plus 3 is also going to get really big as well. So as x plus 3 gets big, the quotient 2 over x plus 3 is going to be really, really small. So as x tends to infinity, this expression is going to get close to 0, and the entire expression is going to get close to 0 plus 5, which is equal to 5. Right? So we can sort of feel just algebraically when you plug in some numbers that this is going to correspond to the horizontal asymptote that we sort of investigated earlier. And also, we can figure out what the vertical asymptote is by just looking at the denominator, because remember, you cannot divide by 0, and what number makes this 0 in the bottom? That's just going to be negative 3, right? So this is going to correspond to the vertical asymptote, right? And y is equal to 5 is going to correspond to the horizontal asymptote, right? So let's just graph those things out. So let's see if we can construct a graph right quick. So x cannot be equal to negative 3, so 1, 2, 3. So our vertical asymptote is going to be here. Y cannot be equal to 5. So this is going to be 1, 2, 3, 4, and 5. All right. So it's going to be y is equal to 5. And this is going to be x is equal to minus 3. And notice we have a negative sign in this expression. So remember, the normal orientation for 1 over x is going to be in quadrants 1 and 3. So when we flip upside down the y values, it's pretty much going to be in the quasi-quadrants of 2 and 4. So we're going to be located in this region up here, and we're also going to be in some region over here where I'm not really focusing on the details of the x and y axis. All right, so let's look at another example on how to sort of sketch the graph of rational functions. So example 2, let's consider the function g of x is equal to 12 plus 3 divided by x minus 5. All right, so again, as x tends to infinity, this is going to tend to 0 as x gets really big. So then we're just going to be left with this number 12, right? So this is going to correspond to our horizontal asymptote of y is equal to 12, right? And we can look at the denominator of our basic rational function and see that x is equal to 5 is going to correspond to our vertical asymptote. The leading coefficient of the rational term is positive, so it's going to have our normal orientation like our parent function 1 over x. So it's going to be in the quasi-quadrants of quadrants 1 and 3, right? So let's sketch out our asymptotes. So we have y is equal to 12 somewhere up there. So y is equal to 12 is there. We have x is equal to 5 somewhere over here. So x equals 5. And our normal orientation. So we're going to be located somewhere over here and somewhere up here. And again, I'm not really focusing on the x and y intercepts and some of the scalings of this. This is just an idea to sort of how this function is behaving on the global spectrum. All right, so I've been making these examples a little bit more easy. In particular, I'm making the numerator a constant function. That does not need to be the case. For example, you can have 5x minus 2 over x plus 3. So this is not at least a basic transformation of 1 over x. So we have to perform a little algebra to sort of get an idea of what is going on here. And the easiest way to do that is via long division. So what I'm going to do is I'm going to divide x plus 3 into 5x minus 2 to get an idea of what the quotient and remainder of this function actually is. So we know x goes into 5x 5 times, and 5 times x plus 3 is going to give us 5x plus 15. And then what I'm going to do is I'm going to subtract those things off, and I'm going to get negative 2 minus 15 to give us minus 17. So of course we know this is the remainder, and this is the quotient. So we can rewrite our function h of x in another way. So h of x is going to be equal to the quotient plus the remainder, negative 17, over the divisor, which in this case is going to be x plus 3. So this is another representation of our original function, which is actually just a basic linear transformation of 1 over x, right? All right, so here is information about our horizontal asymptote, namely y is equal to 5. And our denominator gives us information about our vertical asymptote, in particular x is equal to negative 3. Now without doing the long division, you can usually tell what the vertical asymptotes are going to be for all rational functions, provided that you can factor them out. Right? And our orientation is going to be opposite because the leading coefficient of our rational expression is negative. So it's going to be in the quasi-quadrants of quadrants 2 and 4, right? So let's just sketch that out. So we have x is equal to minus 3, so over here. We have y is equal to 5, somewhere over there, right? And then let's just draw our sketch. So our curve is going to be somewhere up here and somewhere over here. And you can perform some algebra if you actually want to know details about, say, the x and y intercepts if you're interested in looking at them. In the next video, we're going to go through a little bit more details, a little bit more intricate examples of rational functions. This video is just here to sort of introduce to you the main ideas and main components of just basic rational functions. Hope you enjoyed.